All right, so in the previous segment, we saw how computing the direct material time derivative of an object that is defined on the current configuration can lead to a rate that is not objective, and particularly in the context of writing out constitutive relations for the rate of a stress defined in the current configuration, it can prove problematic. Okay? And then what we also did was introduce this idea of what we finally call the Lie derivative, which by construction does not see the effect of rigid motions on the current configuration. Okay? So we'll just pick up from there. So what we have is the Lie derivative, which was pretty much the last thing we wrote in the previous segment. Okay. It is denoted LV of tau if we are applying the Lie derivative to tau. Okay. That L just stands for Lie. The V stands for this idea that if you think about the way we constructed that derivative, we're really sort of recognizing the flow of the material and nullifying the effect of rotations through that flow. The V here is meant to represent the flow. Okay? It doesn't really play a role in the calculations, but it's just in there for notational purposes. Okay. So the Lie derivative again is this one. It is f time derivative of the pullback of tau to the reference configuration, time differentiated and pushed forward. Okay? Let's check that it is objective, that this rate as this Lie derivative, this Lie rate as defined here is objective. Okay? Is it objective? All right. So what that means is what do we expect for it to be objective? If it indeed is objective, we need to check that the Lie derivative applied to tau plus is equal to just the rotation, right? The rotation applied to the Lie derivative of tau. Okay, let's check this. At the end of the last segment, we had established that the Lie derivative of tau plus is essentially f plus derivative of f plus inverse tau plus f plus inverse transpose. Okay, and the whole thing pushed all the way back. Sorry, push all the way forward. Okay, this is what it is. What we showed at the end of the last segment was that this component, this part of the calculation, is essentially derivative, time derivative of s dot. Sorry, not the time derivative of s dot, it is the time derivative of s. Okay? Well, so now when f plus and f plus transpose act upon it, what it says is that okay, since f plus is qf, f plus transpose is f transpose q transpose. Okay, but now what we have in here is exactly the same as f partial with respect to time of, I saw that I did it again. Okay. Okay, so what I've got an under brace on is the same as f acting on the partial derivative of f inverse tau f inverse transpose. Right? okay? But this is just the Lie derivative of tau. So what we've demonstrated is that the Lie derivative of tau plus is indeed Q Lie derivative of tau. Okay, indeed it is objective. Okay, what this means is that it is now meaningful to write a rate equation of this type. Because now we are talking of a rate equation that relates an objective rate of deformation, which transforms as expected, with an objective rate. Okay, both of them are objective. Okay, now the particular form that we have, okay, and that we're going to derive in just a minute from hyperelasticity, is the following. Okay, so what does hyperelasticity tell us? Okay, what hyperelasticity tells us is the following. Okay, let me think of how we should do this best. Okay, hyperelasticity tells us that the Lie derivative of tau is F S dot F transpose. Okay, which is F C contracted with E dot F transpose. Okay, what I'm going to do now is relate E dot to D. Okay, so consider E dot. Okay, and it has the form E dot equals 1/2 F dot transpose F plus F transpose F dot. Okay. So what I'm going to do now here is I'm going to introduce there, I'm going to put in an F inverse F, and here I am going to put in F inverse transpose F transpose. When I do this, I get 1/2 F transpose F dot transpose, sorry, F inverse transpose F dot transpose F plus F transpose F dot F inverse F. All right. So this is 1/2 F transpose F inverse transpose F dot transpose plus F dot F inverse F. Okay. Now when I pull this half on the inside here, what you should see is that this is basically gradient of V plus gradient of V transpose. Okay, this term is gradient of V and that term is gradient of V transpose. Okay? All right? And when the half is applied to that, what we have essentially in the parentheses is the symmetric part of the gradient of V. Okay? So we have F transpose 1/2 spatial gradient of V plus spatial gradient of V transpose F. Okay, but this is D. Okay, our rate of deformation tensor. Okay, so what this tells us then is that the lead derivative of tau is F C contracted with F transpose D F, the whole thing with F transpose. Okay? I'm going to go to coordinate notation now. The lead derivative of tau Aij is equal to F I, okay, C I J K L. I'm going to close parentheses. I know that out here I'm going to get an F J capital J, and inside here I know that I'm going to get a D little k little l. So it follows that here I need to have an F K K, and here I need to have an F L L. Okay, why does all of that work? Let's look at the inner parentheses. Just the way the indices work, observe that this is like F transpose KK. All right? So you see that what I have on the inner parentheses here does indeed give us this term, okay, with free indices uppercase K and uppercase L. Okay, those that uppercase K and uppercase L contract out those two indices, leaving us with free indices uppercase I, uppercase J. Okay, and those are taken care of by F lower I, upper I, F lower J, upper J. Also observe that this is F transpose J, J, which is what we have up here. Okay, so everything works out. Now, of course, we use commutativity, right? All these things move around. So we can essentially write this as F I, F J, J, F K, K, F L, L, C, no underbar, we are working in coordinate notation, C, I, J, K, L. Okay, all of this with, correct, so I'm going to put a parenthesis on this, okay, and leave D little k little l outside. And here we have lead derivative of tau ij. What this operation is doing is that the deformation gradient is pushing forward each index of our material elasticity tangent into the current configuration. Okay? Observe that the capital Ij, K, L are all being pushed forward to little ij, k, and l by f. Okay? This then is our tangent, our spatial tangent in the current or deformed configuration. No underbar again. With indices lowercase I, J, K, L. Okay? And finally, we have our relation for stress rate in the current configuration related to a tensor that that is essentially a strain rate in the current configuration, right? Our rate of deformation tensor. Okay, and little c I j k l is the spatial tangent. Spatial elasticity tangent. Okay? Now observe, even in the case of the Saminon-Kirchhoff model, where our material elasticity tangent is a constant, right? Our spatial elasticity tangent is not constant, right? It is fundamentally a geometric object. The geometry of the deformation makes our spatial tangent fundamentally non-constant. Okay? Even if you start out with something that looks constant to you in the material configuration, that's really only in the material or the reference configuration that it is constant. Not so as the material continues to deform. Okay? So even for Saminon-Kirchhoff, where we have our material tangent, right? This is the uppercase C, equals lambda isotropic tensor isotropic plus 2 mu fourth order identity tensor, right? Even in this case, where this thing is constant, what we see is that little c, which is basically, you can't write little c in direct notation as push forwards of capital C. It doesn't convey everything that's happening, right? So I have to go to this form. I have to go to coordinate notation to write it, to make clear what is going on. Okay, this is always varying with F and therefore with the motion. Okay, so elasticity, when it is described in the current configuration, okay, elasticity, okay, reference configuration, current configuration. Elasticity described in the current configuration is fundamentally nonlinear. There is just no escaping it. And besides, and in addition, it is geometrically nonlinear. That nonlinearity comes in from the history of the deformation and the current and the current evolution of the deformation itself. Okay? All right, so there is a lot of nonlinearity sitting in there. As you can imagine, the spatial tangent can be complex, right? But when derived in this fashion, by first calculating the material tangent and then pushing it forward, it becomes a little easier to compute. All right, we'll stop here for this segment.